So welcome to the final review. It is 12:41, and I'm hoping to finish this review within 2 hours and 20 minutes because I have a meeting at 3. So let's see if we can do it. So here we are going to start with the number 1, where we want to use the rules of differentiation to find the derivative, and we want to make sure to simplify. So we're going to start with part A here, and I'm going to write this in power form. So I have 11x cubed minus 5x to the negative 2, and then plus x to the 1/2 minus 1. And now I want to take its derivative, so I'm going to use the power rule. So I have f prime of x is equal to, the 3 is going to come down. I'm going to get 33, because 11 times 3 is 33x squared, minus, the negative is going to come down, and minus a negative is going to be a positive 10 x to the minus 3, and then plus the 1/2 is going to come down, so I have 1/2 x, and I take away 1 from 1/2, so 1/2 minus 1 is negative 1/2, and of course the derivative of 1 is 0. And so there's the derivative. The rest is some algebra, so I'm going to write this as 33x squared plus 10 divided by, because it has a negative exponent, so it's x cubed, and then plus 1 divided by 2, and because of the exponent is negative, it's going to go in the bottom, so square root of x. And that's my final answer. And so for part B, we do a similar thing. Let me copy it down. So I have g of x equal to 2x plus 9 to the 4th power times 3 minus x to the 5th. And I'm going to use a product rule on this one because I'm taking the product of two functions. So here's my first function, and then next to it is my second. And the product rule says the derivative of the first times the second plus the first times the derivative of the second. And so below this, we can start. And so I have g prime of x is equal to, the 4 comes down, so we get 4, 2x plus 9, quantity cubed, times the derivative of the inside, which is 2, so there's the derivative of the first function. Then I multiply by the second, so 3x minus, oops, not 3x, 3 minus x to the 5th. So 3 minus x to the 5th, plus the first function, which is 2x plus 9 to the 4th, times the derivative of the second. So the 5 comes down, so 5 times 3 minus x, now that's to the 4th, times the derivative of the inside, which is a negative 1. So let's clean this up. The derivative is done. The rest is just some algebra. So I have 8 here. I have a 2x plus 9 cubed, and a 3 minus x to the 5th. And then minus, because I have negative 1, so minus 5, 2x plus 9 to the 4th, all times 3 minus x to the 4th. And so now the idea is pull out what they have in common. So number-wise, they don't have anything in common. 8 and 5 don't have anything in common, but they do have a 2x plus 9 in common. So I want to pull out a 2x plus 9. And the rule is you always pull out the lowest power. So I have a cube and a 4th, so I'll pull out a cube. And they also have a 3 minus x in common, and they have a 5th and to the 4th, so I'll pull out a 4th. And then we play this game. Something goes here minus something goes there. And here I'm going to put an 8. And I have the cube. I need the 5th. So I put 1, 3 minus x. So this times that is equal to this thing above. And then over here I'm going to need a 5. And I'm going to need a 2x plus 9. So now this times that is this thing above. And I can simplify on the inside. 8 times 3 is 24, minus an 8x, minus a 10x, and then minus a 45. And so what am I going to get here? I'm going to get I have negative 18x minus 24 minus 45 is minus what, 21? And so I could even factor out of this if you want a negative 6, and that would be 3x. Oops, I can't factor anything out of there. I can factor out a 3, not a 6. So let's factor out a negative 3. And so I can factor out a negative 3, which this would make this 6x minus or plus 7. Right, so this times this is that. All right, so my final answer would be equal to, and this would be 2x plus 9 cubed with a 3 minus x to the 4th. And that negative 3 I'm going to put out in front, so negative 3. And then here I have a 6x plus 7. And so let's put that in a box. So that's my final answer. All right, so moving on. Let's look at part C. So part C, I'm just going to copy this down. And so on my paper I have h of x is equal to x squared minus 3x plus 1, all divided by x plus 1. And this is going to be a quotient rule because you're taking the quotient of two functions, so I have a high and a low. And remember, it's low d high minus high d low, all over low squared, and away we go. So h prime of x is equal to, and I write down the low function, so x plus 1, times the derivative of the high function, so the derivative of x squared minus 3x plus 1 is 2x minus 3, then minus the high function, which is x squared minus 3x plus 1, and then all divided by my low squared, so x plus 1 quantity squared. And so now the derivative is done. The rest is just some algebra. I want to simplify, so I'm going to multiply these two expressions together. So I'm going to have x times 2x and x times negative 3. So this is going to equal, I have 2x squared minus a 3x. And then I'm going to multiply 1 times 2x and 1 times negative 3, so plus a 2x. And then 1 times negative 3 is minus 3. And then distribute this negative sign through, so I have minus x squared. Minus a negative is a positive, so plus 3x. And then minus a positive 1 is minus 1. And then all over low squared, so x plus 1 quantity squared. So now I combine like terms. So I look over here, I have a 2x squared, and I'm taking off an x squared, so I get 1x squared. I have minus 3x and plus 3x, so the 3x's here are going to cancel, and I'll be left with plus 2x. And then I have minus 3 and minus 1, which is minus 4. And then this is all divided by x plus 1 quantity squared. And we're all done. So that's my final answer. Next problem. So going on, number 2. Number 2, let's use a highlighter here. It says two lines usually intersect at a single point. We want to find the equation of a line that has slope 3 and passes through the intersection point of these two lines. All right, so remember, to find the equation of a line, you need slope and point. We have slope, which means we want to find the point. Once we find the point, we can plug into the slope point form, y minus y1 equals m times x minus x1. So right now we know m is 3. We just need to find where these two meet. And so the idea, and you can graph these if you want. All right, so the graph of the first one, 2x minus 1, means it has a y-intercept here of negative 1, and so it probably looks something like this. And so that's y equals about 2x minus 1. And then this has a second one has a y-intercept of 4, right? And the slope is going down. So my guess would be, oops, let's redo this. So that was a 2x minus 1. This has a slope of, this is y-intercept of 4, and it's going down, so it does something like, whatever, like that. And so that's y equals minus 3x plus 4. And the picture is just sort of a template to help me figure out what the heck do I do. So here's the intersection point. I need that intersection point. Hopefully when you see that they have the same height. And the functions here give the height. So all you need to do is set 2x minus 1, this height, equal to that height, and solve for x. So add 3x to both sides. So I get 5x minus 1 equals 4. Add 1 to both sides. So I get 5x equals 5. Divide both sides by 5, so x is equal to 1. And if x is equal to 1, you can plug into either of these equations, and you're going to get y equal to, let's plug into the top one, so 2 times 1 minus 1, which equals 1. You could also plug into this equation, and you'll also get back 1. And so here's my y value. And so what I'm going to do is take y minus the point 1, equals my slope, which was 3, and x minus my x value, which was also 1. And I'll solve this for y. So y minus 1 equals 3x minus 3. And add 1 to both sides, so get y equals 3x. If you add 1, you get minus 2. And there's my formula, my equation for a line that has slope 3 and passes through this intersection point. Let's look at the next problem. So now I want to find the global maximum or global minimum. Let's get rid of this of this function. Now I can have my calculator running in the background, although I have to do this by hand. If it doesn't specify that I can use my calculator, I should not use my calculator. I should just do it by hand. And so let's hit y equals, and let's graph this thing so I can kind of check my work as I go. So I have 2 cosine of x in parentheses minus x, and I want to look between 0 and 2 pi. And so then I'll zoom fit it, and I'll let the calculator graph this for me and see what I get. And so there's the graph. And make sure you're in radians. Yep, so I hit mode, I'm in radians, so my graph looks good. And so now I'm going to do this problem. And so to find the global maximum by hand, I have to do step 1. I have to find any possible critical points, so local minimums or local maximums really. So find critical points of f. So this is when f prime of x is equal to 0 or undefined. That's the definition of a critical point. And so I take f prime of x, which is equal to 2 times, now the derivative of cosine of x is negative sine of x, so that'll be negative 2 sine x, then derivative of x, so minus 1. Now this is defined everywhere, so defined everywhere. Remember, a function in this course can become undefined if the denominator is equal to 0, if it's a square root or even root, it must be bigger than or equal to 0 underneath the radical sign. And, or, if you're dealing with logarithmic functions, you have to make sure that the expression inside is greater than 0. All right, so we should write those down. All right, can't divide by 0. If it's an even root, it has to be bigger than or equal to 0 underneath there. And 3, if it's a logarithmic function, make sure it's bigger than 0 on the inside. This does not satisfy any of these. There's no denominators, there's no roots, no ln, so it's defined everywhere. Next thing we do is we set it equal to 0, so minus 2, negative 2 sine x minus 1 is equal to 0. And so we get negative 2 sine x, add 1 to both sides, so equals 1. And then sine x is equal to, divide both sides by negative 2, and you get negative 1 half. And we want to figure out for what values of x, when you put it into the sine function, do you get out negative 1 half? And so we have to know a few things about trigonometric functions. First, we have to understand that all students take calculus, which tells us that all the trigonometric functions are positive in this quadrant, so x does not lie in this quadrant. Only the sine is positive here, so x can't lie in this quadrant. And only the tan is positive here, so it could lie in that quadrant. And only a cosine is positive there, so it could lie in that quadrant too. And we have to figure out what this angle is. So to figure out these two angles, so it could be here or it could be there. And to figure this out, what we know are these angles right here. These are called the reference angles. And to figure those, we just have to figure out what value here gives us, sine of it equal to 1/2. And so we did this table. So let's look at the table. So theta, 0, pi over 6, pi over 4, pi over 3, and pi over 2. And we know we have the cosine of theta, and then the sine of theta. And the idea is you have to memorize cosine of 0 is equal to 1, so it's root 4, root 3, root 2, root 1, root 0, divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. And then sine of theta is the opposite, so root 0, root 1, root 2, root 3, root 4, divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. That's a 2 there. And so you see the sine of theta is equal to 1/2 right here at pi over 6. So I know this reference angle is pi over 6, and this is pi over 6. So to find my answers, I know x is going to be equal to, I have basically pi plus pi over 6, so pi plus pi over 6, which is the same thing as 6 pi over 6 plus pi over 6, which is 7 pi over 6. So x could be 7 pi over 6 plus any multiple of 2 pi, so 2 pi n, right? 2 pi n brings me back to the same spot, plus 2 pi plus 2 pi. Or it could be this angle going all the way around to here, which is 2 pi minus pi over 6. And so for that one, you can multiply both top and bottom by 6, so you get 12 over 6, and so that's 11 pi over 6. So comma, or you could have 11 pi, oops, let's just write like this, 11 pi divided by 6 plus 2 pi n. Again, you could start here, you go 11 pi, then plus 2 pi gets you back to the place where you started, plus 2 pi, plus 2 pi. Now, of course, we only care about 2 answers because we're limiting ourselves to this interval, 0 to 2 pi. So all I care about are these first 2 solutions, 7 pi over 6 and 11 pi over 6. And I'm going to make a table as my next step. So let's make a table. So I want to find the global maximum and global minimum, so I'm going to make a table. So table. And it's real simple. My table is my x and then my f of x. And so what I'm going to do is I'm going to start at 0 and I'll end at 2 pi. And I only care about those values, 7 pi over 6 and 11 pi over 6. And I want to figure out basically what's f of 0, what's f of 7 pi over 6, and what's f of 11 pi over 6. And then finally, what's f of 2 pi. And you're going to plug these back into the original function. So the original function, remember, is that function above. So right here, that f of x equal to 2x minus 2 cosine x minus x. So let's plug that in. And let's do it right here. So this is just going to be 2 cosine of 0 minus 0, which equals 2. And I can do this bottom one down here. This is going to be 2 cosine of 2 pi minus 2 pi, which equals 2 minus 2 pi, so whatever number that is. And you can plug in 7 pi over 6 and 11 pi over 6. Now I'm going to use my calculator. I'm just going to trace this. So notice if I hit trace and hit 0, I should get out 2, which I do. And then I can do 7 pi divided by 6, hit enter, and I get out about negative 5.397, so 397, and so that's approximately. And then I can do 11 pi over 6, so let's do that. So 11 pi over 6, so 11 pi over 6 and hit enter, and I get out negative 4.02. So negative 4.02, and I have 7.5. So just doing a bunch of decimal places. And then I can even do 2 pi, so I can hit 2 pi, hit enter. Now it says invalid. Understand why it says invalid. It says it can't figure out how to plug in 2 pi into our function, and that's because in our window it estimated 2 pi. So instead, let's just go to 7, because that's certainly bigger than 2 pi, and I can refit it. And so there it is. And so let's try this again. So trace 2, and then put a pi there. So 2 pi, hit enter, and I get out approximately negative 4.28. And then you simply circle the very smallest and circle the very largest. So let's take a look here. Which one's the very smallest? So it looks like this one is my global minimum. So f of 7 pi over 6 is my global minimum, which is negative 5.397. And then my global maximum happens when you plug in 0 and you get out 2. So this is my global max. You can also simply check this with your calculator. Since you have it up, you can see, yes, the global max occurs here at 0 when you plug in 2 and you get out 2. And then here's the global min down here, which you can check, plug in 7 pi over 6 again, and you'll see it's down here. All right, so the next problem. So in number 4, we want to determine where the function is increasing, decreasing, concave up, concave down, and find any local maximums, minimums, or inflection points. And finally, we'll conclude with sketching the graph. So we're going to follow the same 4 steps we've been doing. And so step 1 is find the critical points of f. So we want to find out when f prime of x is equal to 0 or undefined. So from the second fundamental theorem of calculus, we know that f prime of x is simply wherever you see a t in the integrand, you replace it with an x. So it's equal to x divided by x squared plus 1. And now this is defined everywhere. And the reason it's defined everywhere is because it does have a denominator, but it's never equal to 0, because the denominator is always positive. If you take any number and you square it, you're going to get back a non-negative number. And if you had a non-negative number and a positive number like 1, it's always positive. So you don't have to worry about this case. The second case you might have to worry about is that if you have a square root, it has to be bigger than or equal to 0, and it's actually an even root. But we don't have any even roots. We don't have any square roots or anything, so we don't have to worry about that. And the third condition you have to worry about is you have to make sure that if you have a logarithmic function, it's greater than 0 on the inside, and we don't have any logs here. So we're fine. So it's defined everywhere, and now we set it equal to 0. So set this equal to 0. We'll multiply both sides by the denominator, and it's going to go away because 0 times anything is anything, and you're just going to get back then x equal to 0. So f has one critical point at x equals 0, so we'll do step 2 now. And in step 2, we're going to do a sign diagram for f prime. And so the idea is, here's my f prime. There's one critical point, so there's one at 0, and this is analysis for f. And so we'll do like, let's say f prime of a nice point to the left of 0 is -1, and a nice point to the right of 0 is 1. And so this is equal to, if you plug -1 in for x, you're going to get -1 on top, and then 2 on the bottom, because -1 squared plus 1 is 2. And then if you plug in 1, you're going to get the same sort of thing, but it's going to be positive 1/2. So it's negative to the left of 0, it's positive to the right. Since the derivative is negative, you know the function is decreasing. When the derivative is positive, the function is increasing, so you're going to get a minimum here. And so we can write down the analysis here. We know that for f, it's decreasing from -infinity to 0, and it's increasing from 0 to infinity. And we have a local min. We have a local min at what? At 0, comma f of 0, Right, so let's just write it like this. We have a local min at f of 0, which is equal to the integral from 0 to 0 of t divided by t squared plus 1 dt, which of course is equal to 0, because there is no area. If you go from something to the same something, there's no rectangle to be made. There's no width to your rectangle, so the answer should be 0. So there's my final conclusion for f and increasing, decreasing, local min, local maxes. Now we want to do concavity and inflection points. So that's basically the same steps, but instead of doing for f, we do it for f prime. So now we want to figure out when f double prime of x is equal to 0 or undefined. And so f double prime of x is equal to, and to do this one, we're going to have to go up here and look at our f prime, which is right here. And we'll use the quotient rule since we're taking a quotient there. So we have low, which is x squared plus 1. So x squared plus 1 times d high, which is 1. Derivative of x is 1, minus the high, which is x, times d low, which is 2x plus 0, and all divided by the low squared. So x squared plus 1 quantity squared. And so this is equal to, you're going to have x squared plus 1 minus 2x squared. So let's just write that out. So you have x squared plus 1 minus 2x squared, all divided by x squared plus 1 quantity squared. And that's equal to, then x squared minus 2x squared is 1 minus x squared. And that's so divided by x squared plus 1 quantity squared. Now this is, again, defined everywhere. Right, defined everywhere. Because, again, the denominator can never be 0, because when you square any number, it becomes non-negative, and if you add a positive and a non-negative number, it will always be positive. So you can never get 0 in the denominator because of that. So then we're going to set it equal to 0. So 1 minus x squared divided by x squared plus 1 quantity squared, set it equal to 0. If we multiply both sides by the denominator, it's going to go away because 0 times anything is 0. So you're going to get 1 minus x squared is equal to 0, which implies that 1 minus x times 1 plus x, and let me clear that up. So 1 minus x times 1 plus x is equal to 0. And so that tells me either x equals 1 or negative 1. So these are critical points for f prime. Now be careful when you solve this equation. If you're going to move over the x squared and take the square root of both sides, that's fine. But don't forget to take the plus or minus the square root of 1. And so now in step 4, I'm ready to do a sign diagram for f double prime. So here's my f double prime. And I know I have 2 points, minus 1 and 1, that I found. And I'm doing this to analyze f. And so I'll take f double prime, let's say, of minus 2. F double prime of a point between negative 1 and 1, a nice one would be 0. And then I'll do f double prime of 2, a nice point to the right of 1. And so this is going to equal. Now I'm going to plug it into this f double prime right here. So I'm going to get 1 minus, if you take negative 2 and square it, you get 4. And on the bottom, I have negative 2 squared, which is 4, plus 1, which is 5, which is 5 squared, which is 25. And so this will be minus 3 over 25. And then if I plug in 0, I'm going to just get 1 back, because 1 minus 0 is 1, divided by 1 is 1. And if you plug in 2, you're going to get 1 minus, and 2 squared is a 4, so 1 minus 4. And on the bottom, you get 2 squared plus 1, and you're going to square that, so you're going to get 25 on the bottom. And just like before, you get minus 3 over 25. So it's negative here, it's positive there, and it's negative here. And so that means concave down for f, concave up between here, concave down over here, which means we have 2 inflection points. All right, so for the analysis for f, what do I have? I know f is concave up from minus 1 to 1, concave down from minus infinity to minus 1, union 1 to infinity. And then we have inflection points. We have inflection points at -1, comma, f of 1. And let's clean that up. So that's f of 1. And then also at 1 comma f of 1. And I gotta fix that right above here. This is f of -1, right? If you plug in -1, then this is f of -1. There we go. Much better. All right, so this is equal to then. We have to go back up to your original formula. So remember, we're plugging into f. So that's -1 comma the integral from 0 to -1 of t divided by t squared plus 1 dt. And this one here is equal to 1 comma, same idea. You start here down at 0 and you plug in 1 for x, and then you have t squared plus 1 dt. And we can use our calculators to figure these out. And so these are probably going to round these, so they're probably going to be approximately -1 comma. And on my calculator to do this, I can hit just math, and I can find f and I and t. All right, so let's clear this out. So math, f and I and t, plug in my integrand, so x divided by left parenthesis x raised to the 2 plus 1, in parenthesis, I have to put comma, what I'm integrating with respect to, comma. I'm going to do 0 to -1 first, so comma, -1. And I'm just doing this problem right here, so I get out about 0.35. So my output is 0.35. And so I get that answer there, and that's off the screen. So let's just do it right here. So -1 comma 0.35. Here we go. And then this one's going to be 1 comma, and I can do this one on my calculator too, and just hit second entry. Since it's the same integrand, all I have to do is change this limit. So this limit then went to 1. And then hit enter, and you get out the same answer. So 1 comma 0.35. And so those are my inflection points. So there's that. And then I can do the graph here. So for the graph, all I need to do is plot the important points I found. And in fact, I can get my graph going on here on my calculator to check my work. So over here, I can hit y equals and f and I and t, and I have x divided by, here's my integrand, right? So left parenthesis x raised to the 2 plus 1, in parenthesis, and then comma, I'm integrating with respect to x, comma, goes from 0 to x, in parenthesis. Now my window, because I found my inflection points to go from -1, to be at -1 and 1, and I found a min at 0, I'm going to go from -2, a little bit less than -1, and then up to 2, a little bit more than 1, and I'll zoom fit it, and I'll let this run in the background. And then what I'm going to do is I'm going to plot all these sort of important points. So I found 0 comma 0 to be a min, and then I found this 1 comma 0.35. This is an inflection point. All right, so I and f and min. And then over here, sort of the same place, but on the opposite side, -1 comma 0.35. This is also an inflection point. And you want to connect these so it's concave up. So it's concave up. It's part of a smile. It's a part of a smile. And then it goes concave down. So concave down. Concave down. So it should look something like that. So if you look at your calculator, slowly but surely, you can see on mine, it's starting to look exactly like this picture. All right, but you do all 4 steps, find those sort of important points, the critical points of f, the critical points of f prime, plot those points, and then connect those points with the right concavity, either concave up or concave down. All right, so the next problem we want to do involves finding the domain. So we want to find the domain of this function. And remember, there's 3 things that limit our domain. 1, we cannot divide by 0. 2. We cannot have negative numbers underneath the square root sign, so this has to be bigger than or equal to 0, and this is for any even root. And then 3, if you have an ln function, you have to make sure it's bigger than 0 on the inside. So on this one, the only one it might violate is this, because there are no roots and there are no ln's. So you have to make sure that this denominator is never 0. So let's find out when the denominator is 0. So take the denominator, set it equal to 0, and try to solve for x. We're going to move over the e to the x plus 7. And I'm trying to solve for x, so I need to get those x out of the exponent. So hopefully you think, how do you get x out of the exponents? And you say, oh yeah, I ln both sides. And when you ln both sides, this can come down in front, and this thing can come down in front. So you're going to get x ln of 3 equal to x plus 7 all times ln of e. And ln of e is a nice number of 1. So what you have now is x ln of 3 equal to x plus 7. And you'll move over the x, so x ln of 3, take away x from both sides, so minus x equal to 7. And here's where you're going to get stuck, because you're not sure what to do now, and you have to remember that you have x times something minus x, so pull out what they have in common. So they have an x in common, then you have an ln of 3 here, minus a 1, which equals 7. Now don't try to take 3 minus 1, because it's ln of 3. Right? The 3 is inside the ln function there. So then you just divide by it. So x is equal to 7 divided by ln of 3 minus 1. And so that's what you do not want x to be. So my domain would be equal to all real numbers, so minus infinity to ln of 7 divided by ln of 3 minus 1, union 7 ln of 3 minus 1 to infinity. So this is interval notation. That's what I would probably use. And so that would be my answer. You could also write down, if you really wanted to, all real numbers except 7 divided by ln of 3 minus 1. So all real numbers except that one. So let's take a look at number 6. So in number 6, we want to find the area, or estimate. We want to estimate the area with the left-hand sum, the right-hand sum, and the midpoint sum. And here's our function, and we're going to do it between 0 and pi, and it is going to be 5, so that means we're going to have 5 rectangles, and we want to draw a picture for each sum, and then use our calculator to find the actual answer, if we can. So on your calculator, hit y equals, as we can graph the sine of x. So here's sine of x, and we're going to do this between 0 and pi. So 0, enter, and second, hit pi. And then we'll zoom fit it to get a nice looking screen, nice looking picture, nice looking graph. And so here it is. And so we can copy this down. It looks just like this. It goes from 0 to pi. It starts down here and it goes up. It turns around and then it comes down. And we want to do the left-hand sum, the right-hand sum, and the midpoint sum. So let's do this. Let's do the left-hand sum first. So for the left-hand sum, we're going to need 5 rectangles. Let's split this into 5 pieces. So how do you divide 0 to pi up into 5 pieces? We'll say it. How do you divide up 0 to pi? Divide pi by 5. So you have 1, 2, 3, 4, 5 pieces. And so this will be pi over 5. This will be 2 pi over 5. So each time I just add pi over 5. 3 pi over 5. 4 pi over 5. And the next one will be 5 pi over 5, which is exactly pi. And for the left-hand sum, you're going to start at the left endpoint. So I start at 0, which has no height. And then I plug in pi over 5, which brings me up here. So that's sine of pi over 5 is the height. And then I plug in 2 pi over 5, which is going to bring me up here. And left endpoint, and then it comes down. And then I plug in 3 pi over 5, which brings me up here. Left and come down. And then finally, I plug in 5 pi over 5, and I come down. And I want to figure out all these areas. And I add up all these areas of these rectangles, and I get my answer. So what I'm going to do is I do sine of 0 is the height. plus, and I'll multiply this whole thing by pi over 5 in the end. So sine of pi over 5 plus sine of 2 pi over 5 plus sine of 3 pi over 5. So that's sine of, and then plus sine of 4 pi over 5. And then this is multiplied then, this whole thing, by pi over 5, and that gives us the area of each of these little rectangles. So this is approximately, and we want to do this on our calculator, so take out your calculator and just plug it in. So sine of 0 plus sine of pi over 5 plus, and then sine of 2 pi over 5 plus sine of 3 pi over 5 and then plus sine of 4 pi over 5. And that should do it. And then hit enter, and that's this first expression. Then multiply this by pi over 5, and you get your answer of approximately 1.93. And so that's the left-hand sum. For the right-hand sum, it's exactly the same, but instead of using the left endpoint, you're going to use the right endpoint. So here's the right endpoint, which gives me this height. I go back. I'm going to use 2 pi over 5, and I'm going to go back. Use 3 pi over 5, plug it in the function. That gives me that height, and I go back there. And then 4 over pi over 5, I go back. And then pi over pi, I get no area. And so I want to figure out for the right-hand sum, I do the same thing, but now I have, instead of sine of 0, I start at sine of pi over 5. Right, that's this height. And in the end, I'll multiply by pi over 5 to get this sort of area. And then plus the sine of 2 pi over 5. And then plus the sine of 3 pi over 5 plus the sine of 4 pi over 5 plus the sine of pi. Then all times pi over 5. Now you can check this on your calculator, but you'll get the same answer of 1.93 because all these rectangles, the areas are exactly the same if you think about it. They're just shifted one back, and then this one over here has area 0 is the same as this area over here. And so you should get the same answer. And now for the midpoint sum, it's going to be a little bit different because you have to figure out, it's too big, you have to figure out the actual midpoint. So the midpoint occurs right here, which is in the middle. So that's 0, it's pi over 10, right? To find the midpoint, you take pi over 5 and divide by 2, which is pi over 10. I add pi over 10, so 2 pi over 10, then I get to 3 pi over 10. That's this midpoint. 4 pi over 10, and this is 5 pi over 10. 6 pi over 10, so this must be 7 pi over 10 for that midpoint. 8 pi over 10, and finally 9 pi over 10. And so this is for the midpoint sum. Let's do it right here so you can see what we're doing. And so for the midpoint, you plug the midpoint into the sine function, and you get this rectangle here. The midpoint, so you get then this rectangle right here. Midpoint, so you get that rectangle right there. And again, the midpoint, so you're going to get that rectangle right there. And again, the midpoint, so you get that rectangle right there. And we got to figure out the areas of all these rectangles and add them up. So we're going to figure out the areas of each of these little rectangles. So I'm going to take the sine of pi over 10. I'll multiply this whole thing then by pi over 5 to get those areas, plus the sine of 3 pi over 10, plus the sine of 5 pi over 10, plus the sine of 7 pi over 10, plus the sine of 9 pi over 10, and then I'll multiply that all by pi over 5, and that'll give me my approximate area. So on your calculator, take it out, sine second pi divided by 10, in parentheses, and then we'll add sine of 2 pi, sorry, so it's not 2 pi, but 3 pi, so 3 pi divided by 10, plus the sine of 5 pi divided by 10, plus the sine of 7 pi divided by 10 plus the sine of 9 pi divided by 10 and parenthesis, and I'll hit enter. Now that's not the area. It doesn't become the area until I multiply by this pi over 5, which is the width of these rectangles. So times second pi divided by 5. And so I get out about 2.03. So about 2.03. And for the actual answer, if I want to use my calculator to actually figure out what this answer might be, what is the actual area? So what is the integral from 0 to pi of sine of x dx? I bet you it's equal to 2, because it seems pretty close to that. But we can check it with our calculator. On your calculator, go back to your graph and hit second trace and go down to number 7 and hit enter. And then our lower limit was 0 and our upper limit was pi. And then hit enter, and it'll shade that region and then tell you that that integral is actually equal to 2. And so yes, it's equal to 2. So let's take a look at the next question. A large ladder is needed to do something here, is needed to reach a wall over an 8-foot high fence, which is 8 feet behind the fence that will reach over. So there's a large wall. And then what is the length of the shortest ladder that will work? Okay. So I imagine this is an optimization problem, and we need to draw a picture. So for these sort of word problems, it's always the same: picture, equation, solve, and test if we can. And so on this one, we have a large wall, and we have a ladder we need to reach over an 8-foot high fence. So let's draw the wall. So here's my wall. And in front of this wall, we have a fence. And the distance here, it says, is 8 feet. And the fence is 8 feet high. And we need a ladder to reach over the fence and to the wall. So this is my ladder. And we want to find the min length of the ladder. Okay. And is that all I know? I think that's all I really know. So I'm going to call this length of this ladder, I guess I could call it L if you want. So let's call it L. And I want to find the min length of the ladder, so my equation is going to be an equation for the length L. And so L is going to equal, and so what do I know about the length of the ladder? Do I know anything? I'm looking to see if I can figure out anything about the length of this ladder. Well, I mean, I can do some things. I mean, I know the height. I could use a Pythagorean theorem. I'd really like to use similar triangles, so that's what I'm looking for. So the height is 8, the length is 8, but I don't see anything with similar triangles here. So why don't we call this distance here x, and this distance, this height here, we'll call y. And I know a couple things. What I can try is this. I can try L squared equals, of course, x squared plus y squared. That's something I certainly can I can do. And so I can start with something like that. And the idea is I want to take the derivative, but I can't take the derivative of this thing. For one thing, I guess I should try to solve this for L. So L is equal to the square root of x squared plus y squared. But it really doesn't matter that much that I do this. What really matters is getting rid of that y. So I need to find a relationship between x's and y's. And if I do that, I see I can do a sort of similar triangles. So you can say that y divided by x, right, this height divided by this length is equal to 8 divided by, and then this length right here would be x minus 8. And that's this length. Let's color code that. So we can color this in right here, is x minus 8. That's x minus 8. And so solving for y, this tells me that y is equal to, multiply both sides by x, so I get 8x over x minus 8. And what I'm going to do is I'm going to be kind of tricky here. I don't want to deal with this square root. The square root causes me pain. So if I want to minimize or maximize little l, I could just minimize or maximize capital L and then use that information to figure out what little l would be, right? The little l is equal to square root of capital L, really. And so I can just use this capital L and plug in for y. So this is x squared plus 8x divided by x minus 8 quantity squared, which is equal to x squared plus 64x squared divided by x minus 8 quantity cubed. Very good. All right, so solve. I have a formula for L in terms of x's, so now I can find L prime. So L prime is equal to, and I'm going to take the derivative of this thing, so I have 2x plus, and now this I'm going to use a quotient rule, so I have my low, which is x plus 8 quantity squared, times the derivative of my high, so 2 times 64 is 128, excuse me, x, and then minus my high, so 64x squared, times the derivative of my low, which is 2x minus 8 to the 1, times the derivative of the inside, which is just 1. So I can write it all out if you want. All divided by, don't forget this is what I typically forget about, my low squared, which is x minus 8 squared, which is x minus 8 to the 4th. And so let's simplify, because we should get some nice simplification here. And that's not over everything. Right? Be careful, I just drew that over everything. Right, so this is just over that. So this is equal to 2x, and then plus, I'm going to pull out what they have in common. So they're going to have 128 in common, because there's 128 here, and 64 times 2 is 128. They're also going to have an x in common, and an x, and I don't know why that says plus. Of course, that should say minus. So that's a typo. What do they say? A mistake there. That should say x minus 8. So I can pull out 1x minus 8, and I play this game. Something goes there, minus something goes there. And what's going to go here is an x minus 8, and what's going to go over here, well, you have 128, and you're just missing an x, because you need x squared. And then inside here, these x's are going to cancel. You have x minus x, that's going to cancel, and so you're just going to be left with a negative 8 inside there. And on the bottom, you're dividing by this x minus 8 to the 4th. And so this is equal to 2x, and you're going to have 128 times a negative 8, which is going to be minus, so let's see what this is, 128 times a negative 8, which is that minus 1,024, and you'll have an x divided by, and one of these is going to cancel, so one of those is going to cancel with one of these on the bottom. And so you're going to have x minus 8 quantity cubed. And that's the derivative. And now I'm going to set it equal to 0. So 2x minus 1,024x, all divided by x minus 8 quantity cubed. Set it equal to 0. And so I'll add this expression to both sides. So I get 2x equals 1,024x. So that's an x there. All divided by x minus 8 quantity cubed. I can multiply both sides by x minus 8 quantity cubed, and I'll get 2x times x minus 8 quantity cubed equals 1,024x. I can divide both sides by 2x, and this will tell me that x minus 8 quantity cubed is equal to 612. So I divide both sides by 2x, so the x's will cancel, and 2 divided by 1,024 divided by 2 is that's 612. And then I'll take to get rid of the cube, you take the cube root of both sides, so x minus 8 is equal to, and hopefully, if I did this right, the cube root is raised to the 1 divided by 3. That's the cube root. I should get back a nice number, and I don't. So what? So I'm thinking that something's off, right? So 1,024, did I divide that by 2? 512. Ah ha ha. Yep. So basic arithmetic always gets me. So 512. But remember, the problems I make are usually nice. Right? So you should be able to have nice cube roots. So if I raise this then to the 1 divided by 3, I get back 8. There we go. And so I add 8 to both sides. Now I'm feeling better. I added both sides. 8 plus 8 hopefully is still 16. I've forgotten the units that we're in, so I need to look back up at the original problem. And we're in feet, so that should be 16 feet. But is that what I need to find? So I go back up, and up here it said find the min length of the ladder. So I need to find this little l. What I found was what x was equal to. And so what I can do is I can plug in to this formula right here and find capital L, and then I can take the square root of it to find little l. So down here, let's do that. So I could say capital L, capital L is equal to, and then this would be, let me just copy it down so you can see it, x squared plus, and then this would be 64 x squared divided by x minus 8 quantity squared. So I'm just going to plug in for x what I found. So 16 squared, and then I have plus 64 times 16 squared, all divided by 16 minus 8 quantity squared. And this should be equal to, when you put this into your calculator, what you should get out is 512 feet is what you should get out. Feet, and this actually be feet squared, but let's just erase that. I don't need to put the units to the very end anyways. But you should get out 512. Let's check it because I'm looking at the answer right here. So I have 16 raised to the 2 plus 64 times 16 raised to the 2, not to the 12, to the 2. And then divided by, on the bottom, that's 8 squared. 16 minus 8 is 8, so I have 8 raised to the 2. And I get out 512. And so then little l, which is equal to the square root of capital L, would be the square root of 512. And this would be in feet, because length is certainly in feet. And that's my answer. You can check your answer by graphing this. One way to do it is you could graph, let's just graph capital L, what we found. So we found capital L to be x raised to the 2 plus 64 x raised to the 2 divided by, left parenthesis, x minus 8 raised to the 2. And we can do our window. We found x to be 16, so let's go from 16 to 32. I bet you it'll be a nice looking window. So 0 to 32, zoom fit, and it'll graph this thing. And since it's a minimum, wow, it should go down and come back up. So that was that's not a very good picture. So let me go back, make sure we put this in right. That looks good. That's fine. So let's make our window a little bit better, I guess. So let's go to, the problem is this 8, right? That 8 in the denominator makes things blow up. So let's go from 10 to 32. So you don't hit 8. So that's what's happening. It's blowing up at 8. So 10 to 32, zoom fit, and it won't blow up as much. Ah, that looks nice. And so realize this thing blew up. I put in a 0. I went from 0 to 32, so it blew up at 8 because the denominator is 0 when you plug in 8, so it blew up. So I got rid of that, and you can see that there's a minimum here. To find that minimum, you hit second trace, go down to minimum, and we can do 8 as the lower bound, 32, left bound. Since I can't put in 8, oh, I put in 10. I can't because I didn't go to 8. So 10 was my lower bound, and then did I go 32 was my upper bound. Hit a guess, hit enter. It'll spit out the answer, so 16 and 512. That's what we found. We took the square root of 512 to find little l. So it checks. All right, so my test, I went from 10 to 32. It looks something like this. And then this point was 16, 512. So it checks. All right, so 2 more problems, and I'm going to take a little bit of a break. So the next problem is we want to find the exact area enclosed by these 2 curves. And so the two curves are y equals x cubed plus x squared minus x, and y equals x. So first, I would really like to see what these two curves look like. And of course, you can put them into your calculator. So you can hit y equals and put these things in. So x raised to the 3 plus x raised to the 2 minus x. And then y equals x. So y2 is just x. And then my window, I really don't know where to look. So if I don't know where to look, I just do sort of a z standard, which is minus 10 to 10, minus 10 to 10. And there they are right there. And actually, you can see how they kind of cross a little bit, but I'd like to get a better picture. So to get a better picture, I want to find these sort of intersection points. And what you have to understand about intersection points is that they occur when the heights are exactly the same. So that means take the heights, which are the outputs, so x cubed plus x squared minus x, and to figure out when they're exactly the same means set them equal. So set these two things equal. So I'll move over the x, so I have x cubed plus x squared minus 2x equals 0. So I can factor out an x, so I have x times x squared plus x minus 2 equal to 0. And I should be able to factor this term here, so this is equal to x, and I bet it's what, plus 2 times x minus 1, that'll work, equals 0. And so I see there's intersection points at x equals 0, so either that's 0, or this term is 0, so that's x equal to negative 2, or this term is 0, so I have x equal to 1. If you multiply things together and get 0 back, one of the things have to be 0, so that's where these points come from. And so this tells me where to look, so I'm going to look. If you look at these points here, I'm going to make my window, and I'm going to go from negative 2 all the way to 1. And if I zoom fit that, I should get a really nice looking picture. So there it is. And that's it. So you see exactly where everything happens, where all the intersection points occur. So I'm going to copy this down. So on here it goes up like this, it comes down, it goes back up, something like that, right? And then it sort of connects at these 2 points right there. And this is at minus 2, 0, and that's 1. And I want this shaded region. I'm looking for this area, A. What is that area? And so A is equal to, and there's 2 different areas I need to compute because the curves change, right? So you have basically area 1 and area 2. And the curve on top changes. That's what I was trying to say. So A sub 1 plus A sub 2. And to find A sub 1, right, this is going to equal, so let's go all the way down here. A sub 1 equals the integral from minus 2 to 0. And the curve on top is this one here, x cubed plus x squared minus x. So I have x cubed plus x squared minus x. And then take away the curve on the bottom. So minus x dx, that's A1. Plus the integral from 0 to 1. Now the curve on top is y equals x. So I'll take x, and then I'll take away the curve on the bottom. So I'm going to take away this whole curve. So it's going to be minus x cubed minus x squared, and then a minus is going to be a plus x dx. And since I'm trying to find the exact area, and it doesn't say I can use my calculator, I can't use my calculator, so I'm going to have to do this by hand. So let's simplify just a little bit. So I have x cubed plus x squared minus 2x dx. And then plus the integral from 0 to 1 of x, 2x, so x plus x. So I have 2x minus x cubed minus x squared dx. And now I can use the fundamental theorem of calculus, which says basically find the antiderivatives and plug in the upper and then plug in the lower limit. So I have x to the 4th over 4. I add 1 divided by it. X cubed divided by 3. Add 1 divided by it. Minus x squared from negative 2 to 0. Plus x squared minus x to the 4th over 4. Minus x to the 3 over 3. From 0 to 1. And that's equal to, let's just do it right below it here. That's equal to, now when you plug in 0, you get out 0. So you have 0 minus. Now plug in negative 2. Negative 2 to the 4th is positive 16 over 4. And then if you plug negative 2 into x here and cube it, you're going to get negative 8. So you get minus 8 over 3. And then minus negative 2 squared is 4, so minus 4. Plus, now when you plug in 1, this is pretty straightforward. You get 1 plus 1 minus. So I have 1 minus. One minus 1/4 minus 1/3, and then you plug in 0 and you get out 0. And so this is going to be equal to then, you're going to get a negative, 16 over 4 is 4, so I'm negative 4. Oh, and actually, if you notice here, you can actually cancel these. So notice this makes it a little bit simpler. 16 over 4 minus 4, those cancel. And so you're going to get a negative, which is a positive, 8 over 3. And then plus, now here you have a 1 minus a 4th minus a 3rd, right? So 8 over 3 here. And so we could probably clean this all up. I don't know. You want to get a common denominator? Let's get a common denominator, right? So common denominator would be 12. So I have plus 12 over 12 minus, multiply top and bottom by 3, so 3 over 12, plus multiply top and bottom by 4, so 4 over 12. And so that's going to be equal to, and I guess I should get, why not just get a common denominator on the first one too? All right, so let's get a 12 here. And so I multiply top and bottom by 4, so I get 32 over 12, plus 12 over 12, minus 3 over 12, plus 4 over 12. And so we can do this addition. So 32 plus 12 is what? 44. Minus 3 is 41. Plus 4 is 45. So I get 45 over 12. Oh, and there's a mistake here. So I got another typo. I don't know how that became plus. Right, somehow magically that became plus, which did not give us the right answer. So this should be minus. So change that. That should be minus, which means that should be minus, which means the answer is off a little bit. All right, so the answer is going to be, it's still going to be over 12, but when you add, you have 32 plus 12, which is 44, and then you're going to take away 7, and so that's going to be 37 over 12. And this is area, so let's put units squared on it. All right, so off by a minus sign. So fix that. All right, so the last problem we're going to do is a matching problem. We want to match the following type of function to its appropriate graph by writing the corresponding letter in the space provided. So you have trigonometric function, polynomial, exponential, piecewise defined, rational function. So remember, rational function, we didn't talk a lot about these, but these are the ones that have vertical asymptotes, really. It's a polynomial divided by a polynomial. And then logarithmic function, power function, absolute value function. What I would do is I do the ones that I know for sure, like f. Hopefully when you see f, you know that's a piecewise defined function because there's two pieces. So this one should be f, so it's gone. So I cross it off. This one here, that's a rational function, so if you knew that one, you could put down a. If you didn't know what a rational function was, you'd have to leave it. So let's leave it. Hopefully you know the absolute value function. It looks like a v. It's the example of a function that's not differentiable at that point right there. That's a sharp corner, so it's not differentiable there. It's not smooth. So b is done because I know that's the absolute value. Trigonometric functions shouldn't be too difficult. Remember, trigonometric functions are periodic, so you look for one that's repeating, and that's e. So e is repeating, and so I would get rid of that one. Exponential function, that one shouldn't be too hard. I mean, you can graph it on your calculator if you get, if you're confused, what's an exponential function? Hopefully you say, oh, that's like e to the x. And so I can graph this thing, and I'll just use a standard window when I graph it. And when you graph it, you see it just goes, oops. Well, you see how it works, but I'm going to use a standard window from -10 to 10. And you kind of see what it looks like. So it starts down and it goes up. So you look for one that starts down and goes up, and that's d. So that's the exponential. And so what are you left with? You have a, you have c, and you have g, and you have h. Okay. Hopefully you can figure out one of these. A polynomial is a really nice function. So this is the nice one, c. So that's a polynomial. Now you're left with a, g, and h. Now a logarithmic function you can graph also. So if you forgot what a logarithmic function looks like, just do ln of x, and we can look at the graph. Oh, and you see it looks like that. Now be careful. it's not this one. Notice how it goes below the x-axis, so it's actually g. So that's g. And now you're left with a power function or a rational function. Hopefully you can realize that the rational function is a, and a power function, because this is supposed to be the square root of x, which is x to the 1/2, is h. That's how I kind of work these.